Today, John is speaking about constructing quantum circuits with global gates.
Okay, thanks, Cole. Yeah, so this is a talk based on a preprint I put online in December, which itself is based on a paper by Maslov and Nam from 2018. And basically, it's about synthesizing circuits using a very particular gate set. Let me say a bit more about that. So most quantum circuit synthesis algorithms, like if you start from a unitary or some other description of a quantum circuit, you synthesize with the goal of having CNOT gates or something similar to CNOT gates, like CZ gates, say phase gadgets. And this is fine for many hardware architectures, but not all of them, because the one I'm particularly interested in is ion trap quantum computers. And their entangling operation, so the operation that is actually interacting on more than just one qubit at once, is the so-called Milnor-Sørensen interaction. So what this is physically, if I remember correctly, is you have two ions that are like close together, and then you shine a laser on them, and this laser makes them wobble. But like the way they wobble when they get close, it depends on the state they are in. So that means they sort of get entangled because of that. So that's how you entangle qubits in the ion trap. And the special thing about this is that there's no limit to the number of qubits you can entangle this way. So you don't have to restrict just 2 qubits. You can also restrict, like you can also entangle like 5 qubits or the entire array at once. So like that calls for a very different way to construct these circuits, because you can't just go to CNOT gates. Well, you can, but it's not optimal. So the question is, like, can we use this global gate somehow to our advantage? And the answer turns out to be yes. That's what I'm going to talk about in this talk. So the main result is a compilation algorithm that transforms an arbitrary circuit that consists of phase gates and CNOT gates into a circuit consisting of single-qubit unitaries and global gates. So I think I want to preface this with, since it is the ZX meeting, is that while I do use ZX calculus, it's not exactly essential to the results. But in a sense, it also was, these results wouldn't have existed without it, I think, because when I read the original paper that inspired me to do this, I didn't really understand the circuit equalities they had until I translated them into ZX, and then I could easily generalize them and like get the results I have here. So yeah, I think it's a really cool use case of ZX calculus, but technically, like you don't have to. But I think it's still a cool demonstration of like that it makes it easier to reason about it. All right, so a bit more about the Milnor-Sørensen interaction. Oh, and by the way, if you have a question or something, like feel free to interrupt me. Clarify me. Okay, so some notation. If I have a Pauli string, so a Pauli string is just a tensor product of Pauli operators, like Z tensor X, tensor Y. And I just write like an alpha here for like the exponentiated Pauli gate. So this is the canonical example would be if my Pauli string is 2 Z gates, and then this would give me a phase gadget. Now the Milnor-Sørensen gate acting on 2 qubits is actually the exponentiated XX gate. This looks familiar, but the colors are flipped with regards to the standard phase gadget construction. Okay. And then the global MS gate, so the interaction that targets more than 2 qubits, it just does this operation on every pair of qubits. So if you have 3 qubits, it just does this on qubit 1 and 2, qubits 2 and 3, and qubit 1 and 3. So every possible pair. I distinguish 2 different classes here, which is that if this set of gates it acts on, the set S, can be arbitrary, then I say the interaction is targeted because we're targeting a specific subset of qubits. But if S necessarily has to be all the qubits in the array, then we call this pin target. So then the global interaction is just entangling all qubits at once all the time. So if S can be arbitrary, it's obvious that this gives you like something stronger, or at least as strong as using CNOT gates or using some 2-qubit entangling gates. But if you only use untargeted gates, then it's not even clear a priori that you could do a universal computation, right? Because like it's not clear that you could then restrict your entanglement to a smaller set. But it turns out you can still do this. That's one of the results in this paper. Okay, so some observations about the MS gate. First of all, if we conjugate all the qubits the GMS gate exon, so GMS stands for global Millman-Sorensen. If you conjugate all the qubits at exon by Hadamard's, so you put Hadamard's in front and Hadamard's behind, then all the X Pauli gates become Z Pauli gates. So we get this diagonal gate, and this is just a phase polynomial, particular type of phase polynomial. The second observation is that if we take this interaction strength alpha, so physically this alpha is determined by how long we shine the lasers on the trapped ions. So we can generally we can tweak this to make it the value we want. So if this value alpha is pi over 2, then the GMS gate is Clifford. Okay. In particular, what this corresponds to is that up to local Cliffords, this corresponds to applying a CZ gate everywhere. So if we think about the ZZ gate, so a phase gadget, that this is equal to a CZ gate with an S gate on top and an S gate on the bottom. And if you have a multi-qubit or like a multi-qubit GMS gate, then you just need to apply these S gates more times. But you still get something that's within local Cliffords of just applying a CZ gate everywhere. So that means that like if our metric of interest is the number of GMS gates, then we can equally well work with global CZ gates because it only affects the number of local Cliffords you have to apply it. Okay. Yeah, so this observation that if a global CZ gate, so I'm going to call these GCZ, we can implement those using a single GMS gate on local Cliffords. And usually local Cliffords are cheap, so this is the same cost as just GMS gate. So for the remainder of the talk, I'll be often using GCZ gates instead because like it's the same cost. Okay, so the first algorithm I'm going to describe is that takes as an input a circuit consisting of Clifford gates and non-Clifford Z phase gates. So this is a universal gate set. You can write any circuit using these gates. And the output is going to be a circuit consisting of single-qubit gates and GMS gates, or a GCZ gates, which is like its equivalent. Okay, so the algorithm starts by looking through the circuit, and you take the first occurrence of a non-Clifford gate. So this will be some Z alpha gate where alpha is not a multiple of pi over 2. And then what you do is you're going to take the circuit and you're going to push it all the way to the beginning of the circuit. And you can do this because every gate before it is a Clifford gate, right? And since this is an exponentiated Pauli gate, if I push a Clifford through it, it just becomes an exponentiated Pauli gate with like a different Pauli that's exponentiated. So this is described in detail in the paper by Litinsky in the surface code paper. It's also described by the people from CQC in the phase gadget synthesis paper. Yeah, and just you can take this non-Clifford phase and push it to the front past all the Clifford gates, and you get like some kind of exponentiated Pauli gate. Okay. Then what we do is we take this exponentiated Pauli gate and then we conjugate it by Cliffords again, so that we reduce it to some phase gadget. So generally, this is an exponentiated Pauli gate where the Paulis can be X, Y, and Z. And then we just make it that they're all either Z's or just identities. Okay, so now it's a phase gadget. So it's a diagonal gate. And then the next step is the interesting one, where the global stuff comes into play. And that is we're going to implement this phase gadget using a single GCZ gate up to Clifford garbage. So what I mean is that you get some Clifford gates that are left over that we don't really need, but like they're fine because we can deal with them. Let me describe this with an example of how this works. But are these first two steps clear? Is there any questions about that so far? I'm going to explain the third step. Okay. So an exponentiated Pauli with only Z's and I's is just a phase gadget, which means we can implement it using a ladder of CNOT gates. This is not the usual ladder of CNOT gates, but you can show this is equivalent because this is also you're taking these inputs and you're copying them here, like XORing them here. then you're applying a phase if the value is the parity of the input is odd. Yeah, so this is just like some arbitrary example just to show how it works. We're skipping this fourth qubit. The fourth qubit does not interact with that. Okay, so the way we implement this using a GMS gate is I take a GCZ gate, so a global controlled Z gate, which I apply on qubits 1, 2, 3, and 5. So again, we're skipping this fourth qubit. And again, this GCZ gate is just a CZ gate applied to every qubit pair. Okay. Now we have these Hadamard gates here, and we push this Hadamard through so that these CZ gates become CNOT gates. So as you can see here in the bottom left. So we have these CNOT gates, we have a Z alpha gate, and then we have these CZ gates here. Now, next step is we introduce these pairs of CNOT gates, which just cancel, right? So we can just introduce these. These don't do anything on the circuit. But now I have this dividing line here, because the stuff on the left is exactly what we wanted. This is the phase gadget that we have here, okay? And then the stuff on the right is sort of left over. So these are leftover Clifford gates. So the way I see this is that, because we started with the first non-Clifford gate, right? So everything to the left of this is just Clifford stuff. And then you have a single global gate, and that implements the gate we need. And then to the right, we have more Clifford stuff, okay? So now we can just see this as sort of the dividing line between the compiled circuit, the stuff that is done, and the uncompiled circuit. So I like to think of this in the same way as in the circuit extraction papers, for people familiar, where this is like the frontier between the parsed circuit and the unparsed circuit. Okay. Now this is sort of the crucial observation of the paper. So if this is not clear, then please ask questions now. Okay. So this is implementing this phase gadgets up to Clifford garbage. The Clifford garbage is the stuff here on the right. Then the next step is simply repeating this. So we take the next non-Clifford gate, and we again push it to the left, the same as in the first step, up to this frontier, this blue line that I draw. And then we just repeat the previous step. So we again synthesize it using a single global gate, and we get some more Clifford gates. And again, we push like the next non-Clifford, and we just repeat until we've parsed all non-Clifford gates. And then by design, we are left with a Clifford circuit. And this Clifford circuit still has to be synthesized using global gates. Okay, so I'm going to describe how to do that now. So this was actually already described in this this earlier paper. I really should have cited it here, but it's cited at the end. See it there. So the way that works is we write the Clifford circuit in some normal form. So the other paper used the Gottesman-Aronson normal form. So this is CNOT gates, S gates, CNOT gates, S gates, Hadamard gates, S gates, CNOT gates, S gates, and CNOT gates. Now the observation is that every CNOT fan-out gate, so a fan-out gate is one that, if I'm not mixing them up, is one that has a single control as a qubit and then targets multiple ones. So it's like applying a CNOT on like multiple qubits at the same time. And such a CNOT fan-out gate requires two GMS gates. And then if you think a bit about it, if you have an upper triangular Boolean matrix that you want to synthesize using these CNOT fan-out gates, then you have n-2, like if you have an n by n matrix, you have n-2 fan-out gates, and then you're at the last column, and this last column requires a single CNOT gate. So this requires 2 times n-2 plus 1 GMS gate, so that's where this number comes from. And then it turns out that using this normal form requires 12n-18 GMS gates. So the way that works is one of these CNOT things is a upper triangular Boolean matrix. The other is a lower triangular Boolean matrix. And the other two are just arbitrary Boolean matrices, but we can use a lower upper decomposition. So we decompose this matrix into a lower diagonal, upper diagonal, and then we synthesize these separately. So this is like 4 of these upper triangular stages, and that requires 4 times these 2n-3. Gives you 12n-8. Okay. My contribution here is actually really simple. It's just use a better normal form. So the normal form we use here is the GSLC, so the graph state local Clifford normal form, which we found in the graph theoretic simplification of circuits with ZX paper. This is the paper with Simon Pedri, Ross Duncan, Alex, and me. So this normal form, the relevant bits are, you have a CZ circuit, a CNOT circuit, and another CZ circuit. So the CNOT circuit again uses 2 times this number, and each CZ circuit just uses n-1. So then we get this number of 6n-8. This is like a 2 times improvement over the previous decomposition. Okay. So then combining these 2 steps of writing all these phase gadgets using GMS gates and then the Clifford circuit that's remaining using GMS gates, we see that if you have an n-qubit circuit, which has it consists of Clifford gates and exactly large N non-Clifford Z-phase gates, we can implement this using single-qubit unitaries and at most n plus 6n-8 GMS gates. So this is linear in the number of non-Clifford gates, and it's linear in the number of qubits. Okay. So this is pretty cool because naively, your circuit would contain like CNOT gates, and these CNOT gates can scale like a lot because per non-Clifford gate you can have many CNOT gates. So this is quite a bit of an improvement that you can make over if you have just access to CNOT gates. Okay, so this is all for targeted GMS gates, right? So this is for GMS gates where I can choose which subsets of gates of qubits I'm targeting. So now I'm going to adapt this algorithm so that we can use untargeted GMS gates instead. So GMS gates that target all the qubits at once. So the basis of this is, the basis for this is a generalization of, again, an argument used in this paper by Maslov and Nam, which allows you to use a pair untargeted gates to construct a targeted gate. So I'm going to describe that later. To describe this, we need a few rules regarding phase gadgets. So the first is just if I have a phase gadgets, like we're only dealing with phase gadgets acting on 2 qubits. If I conjugate by knots on one of the qubit wires, the phase becomes minus the phase. If you conjugate on both the qubit wires, the phase remains the same. 2 phase gadgets acting on the same pair of qubits, the phase is add. And if the phase is 0, it's just identity, it doesn't do anything. Okay, these are just standard rules for these things. So what we do then is, so this is from their paper from Maslov and Nam. If we have 2 untargeted GMS gates, so here I'm assuming the qubit array is 3 qubits, but this would work for like any number of qubits. So we just take a pair of these and we put like NOT gates on one of the qubits here. And then if we expand what's happening, so remember this GZZ gate is just applying a 2 qubit phase gadget on each of the qubit pairs. Now, if we look at what happens with these NOT gates, we see that this bottom, this one acting on the first and third qubit gets a minus sign. This one acting on the second and third qubit gets a minus sign, and the stop one doesn't get a minus sign. So get minus sign, no minus sign. And then we just combine these phase gates, we commute them, and we combine them. And we see that we get minus and plus, and plus and plus, and minus and plus. So some of these cancel, and one of them remains. And then, we get a GCZ gate that's now targeted. So now it doesn't act on this last qubit. So a thing I want to say here is that if you look at the original paper of Maslov and Nam, you only see this top thing is equal to the bottom thing, and it's not clear at all why this would be the case. And now just writing this in ZX notation, it becomes like quite obvious why this would be, which I think is nice. The problem with this procedure is so the nice thing is we can repeat this, right? If suppose I started with these GCZ gates acting on 4 qubits instead of 3 qubits, then after this procedure, it will be acting on 3 qubits because you just remove one of the qubit wires. So now if I start with 4 of these, then I can first remove 1 qubit wire, then I put another NOT gate everywhere, and then I can remove another qubit wire. So I can continue to remove qubit wires to make it more and more local, so targeting less qubits. The problem is this is exponential in like how local the gate is. So if it's global on n qubits and I want to make it local to k qubits, it requires 2 to the n minus k GMS gates. This is exponential, which is very unfortunate. And my contribution here is to actually make this linear in the number of qubits you're targeting. And the basis of it is really a simple generalization. So if I start with these 4 qubits GZZ gates, and I put X gates now on more than 1 qubit at once, then we can go through the same argument. But now something interesting happens. So if you look, for instance, at this phase gadget, which acts on the 2nd and 3rd qubit, there's a single NOT gate acting there. So this phase becomes minus. Okay, this becomes minus. It cancels against its partner, and it becomes 0. But if you look at the bottom one, like the one that's acting on the 3rd or 4th qubit, well, it has knots on both of these. So this phase flips twice and becomes the same. So this one actually adds up. So now we get some of these cancel, some of these adds up, and we get a GZZ gate on the top 2 qubits and GZZ gate on the bottom 2 qubits. And the interesting thing is that this works on any number of qubits. So if this was like a qubit array where like I had n qubits here and I had k qubits here, so this I had NOT gates on k qubits, I would end up with like an n qubit GZZ gate on top and a k qubit GZZ gate on the bottom. So I can split these however I want based on where I put knots on the qubits. Okay. Is there any questions about that so far? Okay. So the next step is simply to iterate this. Okay, so I'm going to show you a large diagram. So the goal here is that we can, so I'm just going to focus here on the end result first. So the goal is that we can get any combination of 2 qubit gates here. Okay, so for instance, we can think if our goal is to make like a layer of CNOT gates, like a layer of parallel CNOT gates. So for instance, I can conjugate this with some Clifford gates, some local Clifford gates before, local Clifford gates after, and here to make this the CNOT gates. And then I have a CNOT gate act on the first, on 1 and 2, and on the 7, 8 qubit. So the way this works is again we start with like global gates, and we have these pairs of things. So here I have a pair with NOT gates on the bottom 4. So that means that this one splits up into these 2, and this pair splits up into these 2, and this pair splits up into this one, and the last pair splits into this one. But I have these other NOT gates around. So now these pairs of NOT gates split this pair up into these 2, and this pair is split up into these 2, and this pair this 2. So now we split up again. Now we already have these 2 qubit gates, but now I do another layer so that I can choose which one to cancel. So here I've put X gates here on these 2s. So these cancel because this 4 alpha becomes minus 4 alpha and cancels against this one. Well, these add up. So at this stage, I can choose where do I want my 2 qubit gates to happen. Okay. And so this is an 8 qubit circuit. So this requires 8 GMS gates. Okay. And if it was a 16 qubit circuit, it requires 16 GMS gates. And if it was not a power of 2, it's like you have to do something similar, but like still sort of linear in the number of qubits. And the other method would be exponential. So there the same result would require 128 GMS gates. Okay.
Hey, John?
Yes?
Does this doesn't at all require that you split them in half, does it?
No, you could do it in thirds. And if your circuit was very particular and had like sub-circuits that consisted of fully connected 2 qubit phase gadgets, then you could do this in like a very optimal way. But I'm thinking now about synthesizing things where my goal is to get CNOT gates, so I need these pairs of qubits.
Why couldn't you split it just into the piece that you want to keep and the piece that you don't want to keep, and then do that twice, and then set it up to where the don't want to keep pieces cancel?
I looked at this at some point and it didn't work for me, but I can't remember now why it didn't work.
Okay.
Wouldn't you get like sort of cross connections if you just split it into those two parts. So like in this case, you would have not just those two CNOT gates that you have on your screen, but also like, yeah, connections between the first and the last qubit and so on.
Oh, I see. Yeah. So the point of this is actually we've gotten two independent GMS gates on the top pair and the bottom pair.
Yeah. So yeah, I'm not sure anymore, but I did look at this at some point, and I don't think it worked. But I think what Miriam said, but yeah.
Okay. I'd like to look at this again because I don't see why it wouldn't work.
Yeah.
Oh, anyway.
Yeah, I'll need to look at that. Yeah, I can't think exactly why. Because yeah, they would still be independent, and then the problem is you still need to cancel this like 6-qubit thing. For it. Yeah, not sure. Oh yeah, the problem is, suppose okay, we have this 8-qubit circuit, and now we want to split it into 6 and 2. Well, we can do that, and we get like the 2-qubit one we want, we get a 6-qubit thing we don't want. But now we need to cancel the 6-qubit thing. And the way we want to do that is we need to flip the phases. But we need to flip it in a way that doesn't cancel the first 2-qubit thing and does cancel all the bottom ones. But there is no way in which we can cancel all the bottom ones because there's no configuration of NOT gates that cancels all of them. So we always get some left over. If we can target, if you could change the interaction strength, then you might be able to do this, but I'm not sure.
Oh, I see. Because if I conjugate a single qubit by X gates, it doesn't flip the sign of everything.
Yeah.
It flips the sign of
all the
linearly many of these quadratically many gates.
Exactly.
Yeah. I see that. Okay.
But if you do the first pair with like alpha interaction, so then you get like 2 alpha like on 2-qubit gates and 2 alpha on 6-qubit gates, and then you do like with minus alpha, so then you get a -2 alpha and a -2 alpha on the 6. Then you can apply a single NOT on the top thing, and then it becomes then a 2 alphas. Then you get 4 alpha on the top, but the bottom one cancels. So yeah, that is actually a good observation. That allows you to do this even faster.
Mm-hmm.
Okay.
So is that a general algorithm, or is that just something that you think you can like a trick for this case? Do you kind of see the general algorithm already?
Yeah, I think there will be a general algorithm of implementing a single CNOT gate using 4 GMS gates that's been targeted.
Oh, I see. Okay. Mm-hmm.
Which is quite inoptimal, but yeah, it's a way to do it.
Mm-hmm.
Okay, let me just.
Yeah, sorry, I've got another question actually. So I guess I didn't quite remember from the previous slide, but certainly with your system, sort of you in this example, you're like finally realizing gates with phase 8 alpha, but you had to start out with phase alpha, and presumably as the circuit gets bigger, that kind of cost also increases. So like was it the same in the previous case where like you also have this increasing sort of accuracy that you need in the phases, or? So
the previous case was actually worse because there it became exponentially small, the angles you have to start with. Here the angles become linearly small. So in general, like if you have an n-qubit circuit and your target is alpha, then you need to start with alpha over n, like roughly alpha.
Okay, thanks.
Yeah, that is definitely a problem if you're thinking about thousands of qubits. But like I would hope that if you have thousands of qubits that you're not working with untargeted global gates, because that doesn't seem very
Yeah.
So the result of this is that if I have an n-qubit CNOT circuit of depth d, I can synthesize this with local Clifford gates and at most d 2 to the k untargeted n-qubit gates, and this k is the smallest number such that n-1 is smaller than 2 to the k. So this is sort of this 2 to the k is the smallest power of 2 over n, sort of. And yeah, again, it's like this. You need to make these phases smaller because you need to end up with a Clifford phase in the end. And it turns out that the asymptotic optimal depth of an ancillary CNOT circuit on n-qubits is n over log n. So depth n is quite easy to achieve. It's a simple algorithm to do that. getting depth n over log n is really convoluted and requires like very complicated things. So just to note. And so combining these two observations means that if we have an n-qubit Clifford circuit, because a Clifford circuit requires just a linear number of CNOT steps, we can implement this using low Clifford gates and order n squared over log n untargeted n-qubit GZ gates. Yeah, so in the previous method, you would require an exponential number, and now it's this quadratic, like quadratic-ish number. What I think is interesting is that the asymptotically optimal CNOT count for implementing n-qubit Clifford is also n squared over log n. So this actually doesn't give you any benefit of using CNOT gates, but it's also not a drawback over using CNOT gates. It still has the same count. And perhaps there is some information theoretic argument for why you shouldn't be able to do better than this number or something. I know there is this argument for CNOT count, but maybe there's a similar argument for why you shouldn't be able to do better with global gates. Okay. So this is the Cliffords using untargeted gates. So now the next step is implementing phase gates using untargeted gates, and this is just a simple adaptation of the thing we had before. So these last two steps are the thing we had before, right? We had this GCZ gate acting on the qubits that the phase gate acts on, and then we get the desired outcome up to some Clifford gates. The only change we make now to get this is how we get to this GCZ gate. So now we start with a pair of global gates, and we apply NOT gates to where we don't want to have this qubit, where we don't want to have the GCZ gate. And now we also need to apply some S gates, and then with the same trick, we get the GCZ gate. These S gates make it into a GCZ gate. Now, because I only had a single qubit not interacting, this qubit just doesn't do anything. If there were multiple qubits that I didn't want the GCZ gate to interact with, I would end up with a GZZ gate on those qubits. But that would be a Clifford gate or a set of Clifford gates acting on qubits that like are not important, so that they would just be additional garbage, like Clifford garbage on like the right-hand side. Okay, so this just means we have an overhead of 2 when we want to use global gates in phase gate. So that's really good. So that means that we can adapt the previous result. If I now have an n-qubit circuit and it has big N non-Clifford gates, then we can implement it using untargeted GMS gates, but now we have 2n here instead of n, and we have this O n squared over log n instead of a linear number here. Okay, so conclusion. Let me just put the numbers beneath each other. So yeah, we have let n be the number of qubits and n number of non-Clifford gates. Then in the targeted case, if we're just implementing a Clifford circuit, it requires 6n minus 8. If you want to do an arbitrary circuit, this requires n 6n minus 8. And in the untargeted setting, Clifford requires n squared over log n, and arbitrary, we just get this factor 2 here, and we have this order n squared over log n. Some future questions here is how tight are these bounds? So for instance, if you think on the n is 2 case here, we get 4. I think you should be able to do with 3, but I'm not sure. And this, I think, might be pretty tight. At least there's like linear dependence on the number of non-Clifford gates. Like I'd be surprised if you could do it in a sublinear number of gates. Yeah. And then the other question is like, is there a benefit to allow alpha to vary? And I think I just realized that there is in the case of implementing these Clifford gates. If you can allow alpha, if you have alpha n minus alpha, then you can do some cool things. But the case I'm also interested in is that physically you won't be able to put alpha perfectly. It will only be close to the value you want. But since we're repeating these layers, like can we use this as some form of natural error suppression? So like if you deliberately put alpha a bit too large in one case and a bit too small in the other case, and maybe they cancel in some nice way or have some quadratic error suppression somehow. Yeah, I think that'd be an interesting question to look at. Yeah, that was what I want to say. The first thing here is the paper this is based on. The second paper is the one I've been referring to a lot. So this is Maslov and Nam. This is like the one that I used to get started with this. And this is just some advertising for my latest paper. If I think most people here already are quite familiar with SEDEX, but if you want to learn more or you are unfamiliar, then check out my review paper at the bottom. And yeah, thank you for listening.
Let's thank John. Are there any more questions? I have like a really general question. Have people like use this method of like how many qubits have people like use this like method of that you talked about at the beginning, like where you like vibrate ions?
So I mean, ion trap quantum computing is quite popular. Like I feel like I think it's like the second most well-studied one. Like the first one being superconducting, and the second being ion trap. But like I'm not 100% sure. Alex, do you want to maybe comment on that?
Yeah, these days, I guess it would be at least when it comes to matter-based things. And then there's optics as well, but you don't really have memory there. In the old days, people were doing lots of stuff with NMR, but the noise is a bit crazy, so I think people don't talk about that very much anymore.
Yeah, so so there is quite a few people doing ion trap stuff, and I think, as far as I'm aware, all the ion trap people use Millman-Sørensen. This is like the interaction you use there. I have seen a couple of papers that specifically benchmark the global interactions that target more than 2 qubits, but there is a problem with coherence. And so far, the 2-qubit one has a higher coherence. Although there are like engineering difficulties in getting it to target just 2 qubits. So if they could get the global case to work better, like it also requires less engineering because there's less things you have to focus. I also want to say I only focused here on Millman-Sørensen and ion trap because that's the one I'm most familiar with. But the Nam and Maslov paper also talks about global interactions in superconducting circuits. But I haven't looked at that in too much detail, and I think it's a less popular way of doing things. But so apparently there is also a way of doing these global interactions in superconducting circuits. So like that would be pretty cool. Yeah, I also have to add, I'm not 100% sure like what the engineering requirements are for this like targeted versus untargeted case. Like how hard is it to, like if you want to do a large group of qubits, but a specific larger group? Like I don't know how much difficult this is. Just target all.
So one of the things that the Maslov and Nam paper mentions is that it might not be realistic for all of the alphas to be the same on a global gate. So they also look at a model where the alpha depends on the distance. So they assume that all the ions are in a line, and then the alpha depends on just the Manhattan distance between the two ions or something like this.
Yeah, I think in that setting, what I talked about would be really difficult to get. Like at least things won't cancel this time.
Yeah.
I have a question similar vein about the Thank you very much for the talk. So you talked about untargeted and targeted GMS gates. Have you thought about the case where it's targeted, but you have some limitations on what you can target? For example, if you can only target like 3 or 4 qubits at a time, or you have some architecture constraints.
Oh, right. So that you have restrictions on how many you can target. So I did not look at that. And in general, my methods would not work in that setting.
Okay, cool. Yeah, thanks.
Yeah, because you get phase gadgets of possibly really high error, so you need to target those things. Like maybe if you retard, you could like change the compilation algorithm to try different options each time and see which results in like low connectivity phase gadgets, or like so that you can implement those. Yeah, in general, I don't.
If you had something like 3 targeted Mulmer-Sorensens or something, you could imagine constructing better fan-ins and fan-outs than you could with 2 targeted ones. Like maybe you can do some sort of tree-like construction.
Or did you get some benefit over the CNOT ladders that you have?
Yeah.
Yeah. Yeah, that makes sense. Like if you have a tree targeted, yeah, I think you would need like half of the CNOT count you would need to implement. So there is some benefit.
Yeah, okay, cool. Yeah, we can maybe also talk about it another time. Thanks.
Any other questions? In that case, let's thank John again.